Hi guys, you're welcome to God Academy. This is our first lesson in algebra, which is Introduction to Algebra. In this lesson, I'll be taking you through the fundamentals, the things you're supposed to know for you to have successful algebra course. If this is the first time you are visiting this channel, this is God Academy and we provide useful content like this to support your academic journey. Do well to subscribe, support the journey. So, Introduction to Algebra. We start talking about algebra, we start with what we call the number systems. Number system. So for the whole course of algebra, you'll be dealing with numbers. So for us to get a very good view of algebra, you need to understand the evolution of numbers, the properties involved, as well as some operations and some necessary key things for to know about number system. In the evolution of numbers, the very first number we talk about is what we call the natural numbers. Natural numbers. Okay. When you talk about natural numbers, it's a set of number which has a least number to be equal to 1. So the list of natural numbers, I'm going to have 1, 2, 3 to n. So natural numbers is the first set of numbers we study in the algebra course because it has the simplest of its form, starting from 1. So the least number any natural numbers or a set of natural numbers would have is 1, and it will go to the nth term. From natural numbers, scientists realized there was importance of the number 0. So the inclusion of the number 0 gave birth to the second classification of numbers called the whole numbers. So whole numbers simply added 0 to the set of natural numbers. So I have 0, 1, 2, 3 to infinity or to the nth term. After whole numbers, scientists also realized that you can have, so scientists realized that you can have negative numbers in addition to the positive numbers. So then how do we um, classify depth? So mostly looking at the evolution of numbers, the idea of negativity was introduced through trading. So the concept of trading gave birth to the idea of negativity. You realize that if somebody is owing you, you cannot make it positive. If you are having a product somebody buys without paying, then the idea of debt was translated to negative. So our third set of numbers we call integers. Integers. So integers simply classified both negative and positive numbers. Okay, so integers is simply having -2, so it's start from infinity. So I'll have something like this. I'll have three dots starting because it doesn't have a beginning and it never ends. Okay, looking at natural numbers started from 1 to, whilst whole numbers started from 0, but integers doesn't have a beginning, so I'm going to have -2, -1, 0, 1, 2, and also three dots. Okay, so this is a set of integers just to account for negativity. So just to look at the evolution of numbers here. Now, after integers, we also have another set of numbers that emerge. And this was because there's a need for us to divide. So as I said, the concept of numbers actually emerged from trading. The ancient Greeks and the rest were mostly traders, and they realized that assuming you have 3 mangoes or you have three any products or something, and you have just 2 people to share, you have to divide this. So the idea of division gave birth to what we call rational numbers. So the fourth number system, which we call the rational numbers. Okay, so the rational there is simply coming from the word ratio. So you can see ratio, or it is simply a fraction. Okay, so a set of rational numbers is accounting for the set of numbers where we have it in the form p over q. So having p over q, where q is not equal to 0, okay? So every rational number should satisfy this condition. It should be in the form p over q, where the q is not equal to 0. So with rational numbers, you can have numbers like 3 out of 4. You can have numbers like 1 itself, because any number standing alone can be assumed for 1, therefore can be a rational number. And you can see that from the evolution of numbers, the numbers grew to cover larger spaces. So natural numbers couldn't capture 0, whole numbers came to capture 0. Now integers came to capture negative whole numbers. Then rational numbers are also catering for the fraction. Okay, so rational numbers will cover everything. So every level of the evolution tree, it covers what the preceding numbers couldn't capture. Now let's go to the fifth set of numbers. Fifth set of numbers. So after reaching rational numbers, scientists realized that there were some particular numbers which didn't satisfy the rational numbers, so that you cannot represent them in the form p over q, where q is not equal to 0. There's one thing here you should take note of. For rational numbers representation, it should always be in its simplest form. You can't have 2 over 4, no, because 2 goes into itself 1 and goes into 4 2. This should give us 1 out of 2. For every number to be represented as a fraction, it should be in its simplest form for us to call it a rational number. So scientists realized that there were some numbers which weren't satisfying this condition. Therefore, it was given a name, irrational numbers. So irrational numbers, so that they are not rational. They cannot be represented in the form a over b. Okay, so a typical example is the number popularly called pi. The number popularly called pi, right? Why is pi irrational, or why do we say that pi is irrational, despite the fact that pi is represented as 22 out of 7? Okay, this is a fraction, but why is pi considered irrational? Now let me give you the conditions of irrationality. In rational numbers, you can represent any fraction as what we call decimal. So decimal. So for a decimal, there are two major types of decimals. Either the decimal is repeating, example 0.33333. It will keep on repeating like that. Or the decimal will be terminating, example 0.45, 0.275. These are terminating decimals. If you have a number which is a rational number, that upon its decimal representation, it doesn't either fall within these two, either terminating or recurring, then it means that the number is irrational. Most irrational numbers don't end in its decimal form. The number pi goes forth and forth and will never end. So that you'll be getting different numbers. Okay. Another irrational number we have is what we call e. The Euler's number is also an irrational number. Okay. A typical example of another irrational number is square root of 2. Square root of 2 is an irrational number, so that you cannot represent square root of 2 in the form a over b. So when I classify all these numbers into a single umbrella, it gives birth to what we call real numbers. Real numbers. So all these numbers give birth to what we call real numbers as the bigger umbrella. So generally, we can say that number systems are classified into two major groups. We have raw number systems, and we have what we call the complex number system. Complex numbers. In this lesson, I'm going to take you through the raw number systems alone, which covers all these I've spoken about. Now, we have different representations for these numbers. When you have natural numbers, it's represented as n, but you have some dash in this here. Okay, so those representation, take note of that. We also have whole numbers like that. where you have some double line somewhere. Then you have integers represented as z. The z stands for a Greek word called zalen. Okay, zalen. So integers I, but it's still represented as z because of zalen. Rational numbers is represented as q, quotient. We call it quotient. That's why it's represented as q. Then irrational number doesn't have any representation. So they don't have any general representation. Okay. So that one is like that. Now, for us to learn number systems very well, there are some few I have these two major representation in mathematics which you're supposed to understand. When you see this symbol anywhere in algebra, it implies that for all. So we have what you call mathematical language. Mathematical languages are symbols we use to communicate in mathematics. So that I don't need to write plenty words. I'll just use this symbol inside the curly bracket, and I'm trying to tell you that for all, then it continues, right? Example, for all S, which are members of something, right? So this is standing up for all. You have to take note of that to understand mathematics very, very well. Another one is this symbol. It's like E turned other way around, right? So this one stands for there exists. There exists. So you see that there exists a number S. You simply write the E turned backwards, then you bring your S. So this means there exists a number S. We also have this that I wrote when I was explaining the for all. Like this, the E itself, it's a member of, where S is a member of A, right? So understand these mathematical languages as we proceed. Okay, so right after this, let's look at some operations in the number system. So operation. When I talk about operations, these are manipulations we perform on numbers. And these are basic terms we've learned in our elementary schools. We have addition, subtraction, multiplication, then division. So because we learned it simpler, you may not appreciate how it's grew or how it came by, right? So some operations or our core properties of number systems we are going to look at here, we have what we call the commutativity or commutative property. Commutative property. When we talk about commutative property, we are trying to say that the order of numbers does not change the result. If I have a number, two numbers, let's say two numbers A and B, A comma B, and I want to perform an operation such that if I bring A first, B second, or if I interchange and my result is the same, I say that that set of numbers are commutative, or it's a commutative property. Commutativity works on addition here as well as multiplication only. Take note of that. Only addition and multiplication has commutative property. For example, I'll have 2 plus 3. This gives me what? 5. I can interchange this and write 3 plus 2, and this is the same as 5. It doesn't change the result. That is commutative. So for the multiplication, I can have something like 1 times 2. That gives me 2 times 1 also equals 2. So meaning that the order doesn't change the result. As simple as that. The next one is what we call the associativity. Asso so association. So associativity, right? Or associative property. The associative property is saying that the group of numbers or grouping of numbers doesn't change the result. So here we are not talking about the order, but rather grouping. So associative or associativity deals with three sets of numbers or more than, if you have more than two, right? So assuming that I have three numbers, A, let me list them. I have three numbers, A, comma, B, comma, C. These are sets of numbers in the row number system. Such that if I have an operation where A plus B into one bracket plus C, then this is the same as A outside plus B plus C inside one bracket. Now, associativity or associative property works on multiplication and also works on addition. Okay, so here too we are still on multiplication and what addition. Take note of that. So if I have something like 2 plus 3 plus 4, I can group this as either 2 plus 3 or plus 4, or 2 plus 3 plus 4. So the grouping of numbers doesn't change, but provided we are working within the right okay. This doesn't necessarily work for subtraction and for division anyhow like that. So let's also go to the next one, which we call the distributive property. As the name denotes, you are distributing. Okay, so the distributive property. So for the distributive property, what you are trying to say is we are trying to share or distribute. So multiplication distribute over addition or subtraction. So here you can see we have made mention of multiplication, which is distributive over what? Addition and subtraction. Now let's see how distribution also works. If I have a set of terms which is A, B, C as I listed, and I have A multiplying the expression B plus C, this will give me A times B plus A times C. If I have A multiplying the expression B minus C, I can distribute this as A times B minus A times C. This property helped us to simplify expressions easily. So this is where, and this is why whenever we have algebraic expressions, we easily compute by distributing, by factorizing, by applying all the basic properties which have been listed here. Now let's move to the concept of identity and inverse. Okay, so let's talk about identity and inverse. Now, when I talk about identity, this identity property is a special property within the number system space. And when you talk about identity elements, these are numbers so that if you add it to any set of numbers, you get that number itself. These are numbers. So if I take a set of natural numbers, there is this identity element so that if I add the identity element to any natural number in this world, I'll get that natural number back. There are two major types of identity. We have the first one, which we call additive identity. Then the second one, which we call multiplicative identity. So take note of this. We have additive identity and multiplicative identity. As I explained earlier, identity is simply a number which doesn't have any effect provided the operation is being considered on a set of numbers. So additive identity is simply a number that when I add it to any other number, I'll get that number itself. So let's see, if I have the number 2, what other number when I add to 2, I'll still get 2. That is exactly 0, right? So 2 plus 0 is 2. If I have a number 1 and I add it to 0, I'll still get 1. If I have a number 3 and I add it to 0, I'll still get what? 3. This is what we call identity. So here we can mark 0 here, mark 0 here, mark 0 here, and see that the set of zeros that you see here is what we call the identity. So the additive identity we have in the number system is what? 0. So 0 is an additive identity. Let's check multiplicative identity. Is there a number in the number system so that if you multiply by any other number, you get that number itself? 2 times 1, 3 times 1, 4 times 1. Any number times 1 will give you that number itself. Is that not it? That means the multiplicative identity we have is 1. Take note of that. Is 1. Now, having learned multiplicative identity and additive identity, let's go to what we call inverse. So, inverse, as its name denotes, we are trying to counter, right? So, inverse is simply a number that when you add it to, or when you add a number to its inverse. So, let me say it this way. whenever you add, so adding a number to its inverse, okay, give the identity, as simple as that. So this is in a place of additive identity. So whenever you add a certain number to its inverse, you are supposed to get the identity of the operation. How do we understand this? I made an illustration here that 2 plus 0 is 2, 1 plus 0 is 1, and 3 plus 0 is 3. We are saying that the inverse of a number is simply a certain number that when we add it to this number, we are going to get the identity. In additive identity, our identity element is 0, clearly seen here. So if I take 2, what other number can I add it to 2 to get this 0? It's so simple. What is it? Which is negative 2, right? So the first one, I'm going to get negative. When I add negative 2 to 2, I'll get 0. So the additive inverse of 2 is negative 2. So as we have additive identity and we have multiplicative identity, we have additive inverse and we have multiplicative inverse. So 1 plus 0 equals 1. The the additive inverse of 1 is negative 1. The additive inverse of 3 is negative 3 because when I add negative 3 to 3, I'm going to get 0, right? When you talk about multiplicative inverse is a number that when I multiply by a number, I'm going to get the multiplicative identity. You obviously know that the multiplicative identity is what? Is 1 from here. 2 times 1 gave us 2, 3 by 1 gave us 3. But now I want to find the inverse. So multiplicative inverse is simply a certain number that when I multiply by the number, I'm going to get the multiplicative identity. So what's number that when I multiply by 2, I will get the multiplicative identity 1. So here is simply what? 1 out of 2. So 1 out of 2 times 2, I'm going to get what? 1. When I come to 3, I'm going to have 1 out of 3 times what? 3. I'm going to get what? 1. So multiplicative inverse is simply the reciprocal, or yes, you just reciprocate the number and you get the multiplicative inverse, right? Yeah. So we also have what we call the closure property. The closure property. The closure property is a property which says that an operation is closed on a set of numbers. When I take a set of natural numbers n, okay, I'm going to have 1, 2, 3 to infinity, right? If I take any two numbers within n and I perform an operation, I'm supposed to get a result that will fall within this. If the result doesn't fall within this, it means that that operation is not closed under the natural numbers or set of natural numbers. Let's say addition. Is addition closed on natural numbers? If I add any two natural numbers, 2 plus 3, I get 5. 1 plus 2, I get 3. They'll all be natural numbers. So it's sticked. Let's check subtraction. When I subtract 1 from 2, I get 1. Yes, a natural number. But when I subtract 2 from 1, it gives me negative, which is not a natural number. Therefore, negative is not closed under um, the natural numbers or natural numbers. The same for multiplication. Multiplication is closed because any number you multiply on the, if you multiply 3 times 10, any number, you surely get a number within. As well as division is not closed because 1 over 1 is 1. Yes, it's natural number. But 1 over 2 is half, and that is a rational number. So division is not closed. So this is the idea of closure properties. Okay. Now, this is the end of our first lesson in Introduction to Algebra. See you in the second section where we'll be doing more of mathematical induction and proving. If this is the first time you are being on this show, please kindly subscribe and kindly share to support the mission.